name is Dr. Tasfir Ahmed, and I am going to record the second lecture on graph neural network. The topic of this lecture is graph attention network. So first question is why we need the graph attention. So graph attention is basically to give the importance to the nodes of a graph. For example, there is a node I and these are the nearby nodes, and we have to compute that how much each node is important. For example, node C. So we will have to compute its graph. We will have to use the graph attention network to compute the importance of node C for node I, and likewise rest of the nodes. Okay, so there was a very nice paper in 2018 that proposed this idea of graph attention network. So you can further read this paper. So how this graph attention layer is implemented. So for example, we have an input layer of node features where each node has a feature of h1, h2, and with a feature dimension f. So the graph attention network will work that the each node features it have been transformed from f to f prime. So we will have a new matrix that has a matrix h prime that has a h1 prime, h2 prime, node feature 1, node feature 2, etc. So we're applying the parameterized transformation to every node. We apply parameterized transformation W to each node, and this W has a dimension of f prime by f. So when we multiply it with a node feature I, so we get f prime. So W prime by f multiplied by 1 by f, what we get f by 1 we get is f prime by 1 or f prime. So self attention, we try to see that self attention is an let's say we have an a, and a is input matrix has a dimension of f cross f. So there are total 2f weights, and this a input is multiplied with w by hi, w by hj, and this eij is actually assigns the importance of node j to node I, how the node j is important to node I. So normalize, so this attention, self attention is normalized over all the nodes, considering that how the node j is important to I as compared all the neighbors of the node I. Among all the neighbors of node I, how much the node j is important to I. So it is shown by this mathematical relation. Exponent is numerator and sum of exponent is in the neighboring nodes, exponent is in denominator. So what this alpha is? Alpha is a single layer neural network input and output, and there will be the weights which we have to learn. And more precisely, for example, we have two nodes, node I and node j. So node I, we have w by hi, that will result in hi prime, has a feature dimension of f prime, and similarly for node j we will have a h prime j, we have a feature dimension of f. So we have a feature dimension of f and f prime and f prime. So 2f prime number of weights that we'll have to learn. So these weights, they will go to a leaky ReLU function, which is similar to the ReLU function, non-linear activation function, and then they will be they will be scaled, or they will be normalized, like in the numerator eij in the numerator divided by node j to I in numerator divided by sum of all the nodes of the I. So more precisely, as a dimension wise, if we break down, what we get is that whi, whj, they are concatenated, and so after concatenation, the feature dimension becomes f prime and f prime to f prime by 1, and a has a dimension of 1 by 2 f prime, as we have mentioned above over here. So a has a dimension of 2f prime. So applying concatenation. So then we apply the ReLU function. So this after this multiplication, we get a scalar value, and finally applying this all exponential, we get a scalar values. We get scalar value in numerator, and we get scalar value in denominator. So at the end, we get a scalar coefficient for a node j to I as an attention coefficient. So this is a more pristine or more better representation that alpha, we have a WHJ, node feature J, and they are multiplied with some coefficient alpha, and then we apply nonlinear activation function. So for each node, we have a alpha A, alpha B, alpha C, etc. So this is a single head attention. So we have, just like this, we have a multi-head heads as well. So these multi-heads could be the attention to the age, attention to the gender, attention to the height, or etc. So these different heads, they could be concatenated or they could be the averaged. So this is the same notation, but what we extra have, we have a k. K is an each head that we are including, and at the end all heads are either concatenated or all the heads, they are averaged. As the original paper suggests, that during in between the graph neural network, these heads are concatenated. At the last layer, these heads are averaged. So here, this is the message passing message passing implementation in the PyTorch, where we have the message at layer k minus 1, and then we compute a nonlinear activation function, which and apply a summation over it, and then passed to a second nonlinear function. So this is the message, and the message is aggregated over some or aggregation function, and then an update is applied on this message, and then from layer k minus 1 to layer k, the message is updated. So message, and then apply nonlinear function on it, and after applying the summation or concatenation, and then update that message. So this message passing is either updated, has aggregation, mean, average, or max, or this is either the messages from source to target, or target to the source. So this in PyTorch for message passing, these are the different methods that are being used in the message passing class: aggregate method, or a message method from node J to I, source to destination, or destination to source, or message propagate, and then the update message update method as well. So this is the glimpse of a code that is being used. So in the PyTorch GCN, so message passing. So initialize the class as an init method or super method. Then there is the forward message, and then they compute the message. So this is the another implementation wise. So we have a node J at k minus 1, and this for node J. To node I, the importance or the attention is computed, that is as a message, and this message is then aggregated and then passed to the next layer. So for this is the same idea more or less, that we have forward pass, we have the message, then we integrate or sum up. So in this case, that is this is a snippet of code that we will discuss in the next video. So the idea is that we first introduce the self loops, and then these self loops you go to the linear transformation to node feature matrix. So this is node feature matrix, and this node feature matrix has been initialized above linear transformation, linear layer, and then compute the normalization function. And the number 4 is the normalize those node features, and then compute the sum up using aggregation or summation or etc. So this is the PyTorch implementation of this GAT. So this was the overall concept of it. Next, we are going to go into PyTorch implementation. I have already run this code. You can use this code to run this file. So importing PyTorch and different libraries that are required. So here, this is the basic structure of a GAT layer. So there will be the init function, and there will be the forward pass So and let's start from the forward method, and there is the linear transformation h I multiplied by w that will go into h I prime. So w will be f prime by f, and h I will be node features f. So and initially we consider that we have a five input features, and we have two output features, and there are three nodes. So for and this is the initializer, and is that Xavier initializer is used. So introduced nodes as a random nodes, and we apply a mathematical multiplication on it, and this is the after the transformation, the input node features, they will get into feature dimension of 2. Initially they have the 5 feature dimension, but after the transformation they have 2 feature dimension. Feature dimension of each node becomes 2. So we have a node hi and node hj. So it has a f prime and f prime, both have a feature dimension f prime and f prime, and so there are actually a 2f prime. So since we have two nodes, so we have our feature dimension will be 4 by 1. So these are the four coefficients that we'll have to learn for each node. So again, this is attention message pass attention mechanism. So we apply the leaky ReLU function on it. So input matrix. So this input matrix, we compute all the combinations of this input matrix. So node A, node B, and node C. So computing all the combinations of input matrix. So there are the 3 by 3 and multiplied by 4. Each row has a 4 entries. So leaky ReLU apply the E as a mathematical multiplication of input and attention coefficient, and attention coefficient multiplied by input, and then we apply as a mathematical multiplication between them and apply leaky ReLU on it, and then we get E. So this E, we get this a shape of a shape of input and shape of then we squeeze the shape. So we have the print the shape of input and shape of E, and this is input has a shape 3 by 3 and by 4, and attention has a shape of 4 by 1, and when we multiply them through math and then we get 3 by 3 by 1, and then we squeeze them to dimension of 3 by 3. So this is the E matrix. So that has a kind of attention between them, and then we compute using E, we compute the attention mask. So we apply the a random initialize function, and then a zero vector which has the zeros in all the adjacency in all the E positions, and then we compute the attention mask using the adjacency matrix such that if the adjacency matrix has a 1, then we get the value from E, and if the adjacency matrix is 0, then we get a value of 0. This is zero vector has a values of almost 0. So for example, this is adjacency matrix has 1, so this is the value of E, and this value of E will be copied over here. And for this adjacency matrix, so this is corresponding E value, but we will not use this. We will get a value from zero vector, so minus 9 raised to the power 15 is copied over here. So this is the attention mask that is being used. So this attention mask is multiplied with H, and it becomes H prime. So we have attention mask, we have H prime. So this is the representation of H and H prime, and we can see that after multiplying with the attention coefficient, the H has the value of H prime has been changed from H. So this is the build the attention layer in Pytorch. So this is we build the attention layer by ourselves, but we can use the built-in attention layer as well. So where is the GAT attention layer, init function, and forward pass. function. So considering this, we import the we instantiate the class GAT layer, Pytorch class GAT layer, and this is init function has input features, output features, dropout layer which is zero point 0.6 as the paper says, and value of alpha which is zero point 0.2 as the paper says, and then concatenate is concatenate, and here is that use the initialization of the weights, and this is the leaky ReLU function. So forward pass, we compute the linear transformation between of the nodes, and then attention mechanism, apply attention mechanism, compute E for A using attention mask and A input, and this is attention is computed, and then H prime that is being computed. So this is the way that H prime it comes. So we use this then we use this attention of GAT attention layer in our problem solving. For example, we apply this to Cora dataset. We import the Cora dataset. We import these GAT attention layers, and this Cora dataset has 7 classes and number of nodes. There are 1433 nodes, and then we use this GAT attention layer, GAT attention layer in layer 1 and layer 2. So layer 1 we have multi-head attention, and these multi-heads are as a concatenate, and the final multi-heads, they are not concat, they are by default are the concat, but they are the average over here. So forward pass, we have the edge index, we have the input layer, so we use the P is equal to dropout layer of 60%. So when we apply, so this is the GAT function that we are going to use. So we are going to use either CPU or GPU depending upon the availability. We put both the data and the model on the device, either CPU or the GPU, and this is the Adam optimizer. And we train our model for 1000 epochs, and we track this loss, and it is pretty fast, and the loss gradually begin to decrease. And after 1000 epochs, we try to we print out the accuracy of the model, and it is 82.3%. That is pretty decent. So this is the way that this is the basic idea of the graph attention network, how the graph attention works. So basically, this graph attention, it takes the it computes the importance of the neighborhood nodes that are important for a node I. So in this way it works, and we discuss basic idea, its conceptualization, and a PyTorch implementation. I hope it will be helpful for you. And in the next lecture, we will come with more and exciting videos. So that's all. Thank you so much.